what we looked at before was spatial resolution. And when we talk about spatial resolution, as we pointed out before, it is the ability to locate 2 points as two separate points, and they can be either axial resolution or lateral resolution. Now we're looking at temporal resolution. And temporal resolution, when you look at when you do your two-dimensional echo, or you do your M mode, you'll see something, we'll call the frame rate, and it is the rate at which you have, the frames. So it is when we talk about temporal resolution, it's a time from the beginning of one frame to the next frame. Okay? It is the time from the beginning of one frame to the next frame. So it's the frame rate. So when you see an image is really a series of lines or ultrasound waves, okay, or scan lines. So to get an image, you need a series of scan lines, which is just incident wave and reflected wave, because the only way you're going to see an image is if you have an incident wave and then the wave is reflected backward and you get an image. So each line in your in your frame represent an incident wave and a reflected wave. Okay, that is, it's it's really incident and reflected. Each frame is created by repeated pulses that form the scan lines, and we usually represent it like this. So this would be, say, one frame. Okay, so it is, again, the frame rate is a time from the beginning of one frame to the next frame. So this would be a frame. This is a frame, and then the frame is made up of these scan lines. These are what we call the scan lines. But each of these lines represent an incident wave and a reflected wave, because when you turn your transducer on and you produce the ultrasound wave, when it's produced, will have to travel to the structure. That means it's incident. So it's an incident wave. It travels to the structure and then is reflected back to the transducer. So each of these lines represents an incident wave and a reflected wave. It goes forward and then it comes back. So that's what each of these scan lines represent. So this is what we call a frame. All right. And the frame rate is the time from the beginning of one frame to the next. All right. So again, this is our scan line. Each of these lines represents an ultrasound wave traveling to the structure and coming back to the ultrasound probe. All right. So the ability of an ultrasound system to distinguish between instantaneous events of rapidly moving structures. So if you have rapidly moving structures, you need something that's going to give you a very high temporal resolution for you to image that structure properly. Okay? So a high frame rate, hence your temporal resolution will be very good. So the higher the frame rate, the higher the temporal resolution. Okay? So you try and get that concept. And when we talk about a sweep, it is a movement of an ultrasound beam through an angle. And the angle may be 30 degrees, it may be 45 degrees, it may be 60 degrees or 90 degrees. So, it's a movement of the ultrasound beam through an angle. That's a sweep. And most of what we do, we use a sweep speed. Okay, so we usually talk about the sweep speed. Most of what we do in echo, we use 50 frames per second, and we usually write it as FPS, frames per second, 50 frames. So again, a frame is represented as, so this is one frame, okay? Frame consists of a number of scan lines, and it's in an, the sweep angle then. The sweep angle may be 30 degrees, so this is this angle right here. It may be 30 degrees, it may be 60 degrees, or 90 degrees, okay? So that's the sweep angle. And then you have the concept of the frame rate, 50 frames per second. That means you're going to get 50 of these frames every second. So again, each frame, this is a frame, you have these scan lines, and the scan lines represent ultrasound wave going to the structure and coming back to the transducer. All right. So let's look at it in a mathematical term. If we're scanning at a depth of 15 centimeters, all right. So the structure is 15 centimeters in depth. Again, if we look at a frame, just take out a frame, the distance from the transducer to the object and coming back. So each scan line represents ultrasound wave going to the structure and coming back to the transducer. So if you scan at a depth of 15 centimeters, your ultrasound wave is going to travel 15 centimeters to and 15 centimeters back to the transducer. So the total distance travel will be 30 centimeters. We know that the speed of sound in soft tissue is 1540 meters per second. Okay? If we want to convert everything to similar units, then 1540 meters per second. If you multiply it by 100, then you get 154,000 centimeters per second. So therefore, we know that velocity is equal to distance traveled over time, or speed is equal to distance over time. So we can find the time that it's going to take. We can find the time that it's going to take the ultrasound beam to travel to the structure and back to the transducer by just rearranging this equation, because time is going to equal to distance divided by speed or velocity. So that would be the time is good. So when you have your frame and you have these scan line, you can find how much time it's going to take the ultrasound beam to travel to the structure and come back. So again, time is equal to distance divided by velocity or speed. And the total distance the ultrasound beam is going to travel is 30 centimeters. This is the speed if we convert it to centimeters per second. So it's going to take 0.000195 seconds or 0.195 milliseconds for the ultrasound beam to travel to the structure and back to the probe. Okay? So each scan line is going to take this amount of time. Each scan line is going to take 0.195 milliseconds. Okay? So if you have a sweep speed of 50 frames per second, sweep speed 50 frames per second, remember we show you what a frame looks like. So every second you have 50 frames. Okay? That is 50 frames every second. Then you will have 50 frames in 1,000 milliseconds, because 1 second is 1,000 milliseconds. All right? So the time it's going to take for one frame. You want the time it's going to take for one frame. Remember what a frame looks like. The time it's going to take for one frame is going to be 1,000 divided by 50, which is 20 milliseconds. So each frame is going to take 20 milliseconds. 20 milliseconds. But I showed you that each scan line is going to the time it's going to take for each scan line is 0.195 milliseconds. So you have the time it's going to take per frame and the time it's going to take for one scan line. So the number of lines per frame, simple math, this is the time it's going to take for one frame, time it's going to take for one scan line. So the number of scan line per frame is 20 divided by 0.195. So in this frame, you're going to have 102, or call it 103 lines per frame, or 103 pulse per frame then. Remember that each scan line in the frame is the time it's the pulse that goes, or the ultrasound wave that goes to the structure and comes back. So you have 103 lines per frame, okay? Or pulse per frame, okay? So the pulse repetition frequency, the definition for pulse repetition frequency is the number of pulse per second. The number of pulse per second. That's a definition for pulse repetition frequency. So the number of pulse per second, because you have 50 frames per second. So the time it's going to take for one frame, the number of lines per frame is your 20 divided by 0.195. This is the number of lines, okay? Number of lines. So the number of lines are the number of, the number of lines is the same thing as the number of pulse, remember? Because each line represents an incident wave and a reflected wave. So the pulse repetition frequency, which is the number of pulse per second, all you do, you multiply your frame rate by the number of pulse. And this is the amount of pulse you get per second. So you can work it out from first principle to get your pulse repetition frequency. Again, remember that pulse repetition frequency and pulse repetition period inversely related. So 1 over your pulse repetition frequency is going to give you your pulse repetition period. So this is our frame, one frame. This is one frame, and the frame is made up of scan lines, okay? And we just look at if the frame rate is 50 frames per second and the scanning depth is 15 centimeters, we work out the time it's going to take for each scan line, and then we also work out the number of scan line per frame. All right. So if you have these scan line in a 30 degrees angle, 30 degrees scan angle. So if you have 103 scan lines in this 30 degrees scan angle, then for each degree, just simple math, each degree will contain 3.42 lines. Okay? 30 degrees, and you have 103 lines in this 30 degrees. So each degree will contain 3.4 lines, or scan lines. If you increase your scan angle, then you see that each degree will contain a less amount of your scan lines. So if you decrease your scan angle, you improve your temporal resolution. If you increase the scan angle, you're going to decrease your temporal resolution, because you're going to decrease the density of the scan lines. Okay, so the line density, you can decrease your line density by increasing the scan angle, and you can work it out mathematically, as opposed to your line density will be greater at a smaller scan angle. Okay, so decreased line density results in decreased image quality because you're going to decrease your temporal resolution. And we show you how you work that out mathematically. So you decrease your line density by increasing the scan angle. You can also increase the line density. You can also increase the line density by decreasing the sweep speed, and we're going to show you that. So if you decrease your sweep speed from 50 frames per second to 25 frames per second, so you decrease your sweep rate or sweep speed. So then in each, so this is 25 frames per second, 25 frames in 1,000 milliseconds. So each frame or each sweep is going to take 40 milliseconds. Doing our same math at a scanning depth of 15 centimeters, the total distance traveled is going to be 30. So the time it's going to take for each of your scan line is 0.195 milliseconds. Okay? And the number of line per sweep is 40 divided by that. So you increase the line density. So you can increase your by decreasing the sweep speed, you can increase the line density and hence increase temporal resolution. Okay, so the line density so you can also increase the density, that is the line density, by decreasing the depth. So not only decreasing the sweep speed, so so you can increase line density by decreasing your scan angle. You can increase line density by decreasing your sweep speed. You can also increase line density by decreasing the depth of scanning. So instead of scanning at a depth of 15 centimeters, if you scan at a depth of 10 centimeters, then the total distance traveled to and from the tissue is 20 centimeters. The speed of sound in soft tissue is still 154,000 centimeters per second. And if you rearrange your equation, the time it's going to take for each of the scan line is 20 divided by that, which is 0.130 milliseconds. That's the time. You say you're scanning at 50 frames per second, but it's that the depth is a smaller depth. Then 50 frames per second. So one frame is going to be 1,000 divided by 50, which is 20 milliseconds. So this is one sweep or one frame. It's going to take 20 milliseconds. The number of line per sweep is 20 divided by 0.13, which is 153.8. So you have more lines per sweep by just decreasing the depth. So you can increase your line density by decreasing the scanning depth. So you can increase your line density by decreasing the scan angle, decreasing the sweep speed, and also by decreasing the scanning depth. All of these things improve temporal resolution. When we did M mode, a long time ago, we usually use we used to, when we had no image at all and it's just M mode ultrasound. It's not uncommon for us to use a frame rate of 3,000 frames per second. Okay, currently we'll use probably 1,000 to 3,000 frames per second. Whereas when you're doing two-dimensional echo, we use 50 to 100 frames per second. So you see, M mode has much higher temporal resolution than your two-dimensional echo. So for fast-moving structures such as the mitral valve, it's best imaged using M mode, which are much better temporal resolution than your two-dimensional echo. What I would do is I would go over the calculation of these temporal resolution stuff, because they're going to ask you in the exam what are the things that will improve or increase temporal resolution. And as we showed, by decreasing the scan angle. So if you decrease the scan angle, if you um, decrease the frame rate, if you decrease the depth of scanning, so all of these things will improve your temporal resolution. Okay, again, with the line density, each line in your sweep, or each line in your frame, represents a pulse. It's an ultrasound wave traveling to the structure and coming backwards. All right. So you just need to go over it and try and understand the concept of temporal resolution, which is different from your spatial resolution. All right, so when we talk about dynamic range, when you look at your ultrasound machine, you're going to see DNR or DR. It's really what it means is dynamic range. And it is the ratio between the largest and the smallest ultrasound signal. And it is usually measured in decibels. So a large DR is good, a large dynamic range is good. And when you look at your grayscale, you're going to see a series of bright and weak echoes, which give you varying shades of gray. Okay, so it's that's what we talk about dynamic range, and you can increase your dynamic range by increasing compression. So on the older machines, you will see there's a compression button there, and you can adjust that. So if you increase the compression, then you increase the dynamic range. Remember, a large dynamic range is good. It just gives you the ratio between the largest and the smallest ultrasound signal, and it's measured in decibels. So high dynamic range, you get more shades of gray, a low contrast image. Low dynamic range, then small difference between the shades of gray. So again, on the machine, you're going to say dynamic range, DR, DNR, or just compression. Just give you an idea, the dynamic range of 35 decibels. You can see you have, it's difficult to see the different background, because you don't have much distinction between the varying shades of gray. Whereas a larger dynamic range, 65 decibel, you can see the different shades of gray a little bit better. Signal to noise ratio, when you look at the machine, SNR, signal to noise ratio, which means the ultrasound wave being measured to that signal is the good ultrasound wave, and then the noise is those waves that you really don't need. So you and of course it affects the image quality. Okay, you want to have a greater signal to noise ratio. So signal is basically the ultrasound wave that you want, as opposed to the unwanted ultrasound wave, which is the noise. So you want a larger signal to noise ratio. Okay, so the noise, undesirable ultrasound wave interference, it affects image quality. So you want greater signal to noise. All right. So large signal to noise ratio is good. It is also measured in decibels. So ratio higher than 1:1 indicates more signals than noise. All right. We're not going to spend too much time on that. And then when we talk about gain, when you look at your ultrasound machine, you'll have different type of gain buttons. So the gain is similar to brightness. You can improve image quality by adjusting the gain. You get what it does is it amplifies the returning signal. Remember that structures, deep structures, because of attenuation, the returning signal is going to be weak. So you want to amplify those returning signals. So you regulate the strength of the echo. So if you look at this ultrasound, you can see the distant structures. If you look down here, the distant structures down here, you have this big dropout. This the atrium doesn't image very well. But if you adjust your gain, then you can see the atrium much better, because you the returning signal, you can amplify the returning signals from deeper structures, so you can see them better. On the machine, you will have the TGC button, time gain compensation button. You can have overall gain. So on the machine, you have overall gain and you have your TGC. Your TGC is what's gonna, so if you look at this image, you see that the poor image is for the distal structures. This looks pretty good. You can increase the overall gain. It's gonna cause everything to look bright. Whereas you could just adjust the TGC to just improve these distal structures. Okay, so the time gain compensation, the signal loss from deeper in the tissue because of attenuations. Remember, deep structures, you're going to have signal loss because of attenuation. So you can improve on your signal loss from deeper tissue, from deeper structures in the tissue, and you just adjust and compensate at each depth. And what it does is it really accounts for tissue attenuation in deep structures. So again, looking at this, you can see the weak signals in the distal structures in the atrium. So by just adjusting the signals, the return signals to deeper structures, then you can see your atrium much better. Okay, you don't want to increase your overall gain, because you're seeing the more proximal structures, you can see them fairly well. It's just the more distal or the deeper structures that you're not seeing clearly. So adjusting the TGC, you can see the deeper structures. All right, and your TGC button looks like this. So once you adjust it, you can move from superficial to deeper structures, and you just adjust it. You're just going to put in you adjust for the image that is deficient. Okay, time gain compensation. So we're going to stop here, and we will finish up with